So my name is Bao Pham, and I went out to MDRS to do a project on simulating resistance and spacesuits at the Mars Analog. And my advisors for the project were Dr. April Andrews and Dr. Bernard Smith. So before I begin, or get started in earnest, I just want to talk a little bit about the Mars Desert Research Station. So it's 2.5 stories, and it's a luxurious 260 square feet, and it has 6 bedrooms and 1 bath, and it's in the middle of nowhere. And as for the rest of Mars, well, it wasn't the friendliest environment because here we were caught in a sandstorm while we were out there. And well, there weren't many things around Mars, or around Mars except for rocks. As you can see, there are just a lot of rocks everywhere. And every single time we had to go outside to anything at all, we had to get into these simulation suits, which were overalls, and there were these 40-pound packs that we would have to put on. So it was pretty cumbersome. And we would have to do that each time that we wanted to go outside to do anything. And that's not the rock. And so while our group was at MDRS, we lived in simulation. We did EVAs, and there was a set of labs that was set up by the school that we tried to do. And we all had individual projects that we all worked on. My project, it was actually suggested by Kurt Chankaya. He was interested in seeing how resistance in spacesuits affect people, because currently the simulation suits at MDRS don't have any resistance in them, but in regular normal spacesuits, there's some resistance because you're in a bladder of air, and so there's something that inhibits your movements. And my project was to simulate resistance, or find a device and method to simulate resistance in the suits. And you might ask, why would you make things more difficult? And things were pretty difficult. As you can see from the picture, my water pack wouldn't work, so it leaked all over the front of my suit, and I couldn't keep my cap on, and there was condensation on the helmet, and it was unbelievably hot and cold at the same time because the helmet was hot, but if you have water on yourself in 40-degree weather, it's pretty cold. So it was already pretty difficult as it was. MDRS is a close analog of Mars because you live in a HAB, you go outside in simulation, and there's nothing around you. And MDRS itself was built with the notion of living in Mars with the current technology of today. And the current technology today has resistance in their spacesuits, which was why I wanted to do this project, because adding resistance to the suits makes for a more realistic simulation. There are 2 different suits involved. The modern spacesuit has an operational pressure of 4.3 psi. Back whenever they had the Apollo suits, they had an operational pressure of 3.75 psi plus or minus 0.25 psi. And so we come to the point where I did the calibrations, which was pretty simple because psi is just pounds over square inches, and which is just force over the area. And so whenever I was trying to determine the area, I measured the circumference around my shoulder, and I came up with 19 inches. And originally, I measured between my elbows and my shoulder to come up with the distance to try to determine the area that I needed to use in my calculations. But it seemed a little bit too big. So it came to me that I should use the area across the joint instead, so I trimmed it down to 1 inch, which makes slightly a little bit more sense. And so what I came up with was I needed around 71.25 psi force. So whenever I tried to do my calculations, I needed to come up with the amount of force that I needed to put in on the suit over the joints to come up with the correct PSI. And for my design, for the knees, or for the elbows, what I did was I took a 30-pound band and a 5-pound band, and that put 70 pounds of force across the joint, which mimics about 3.68 psi, and that's the applied force on the joint. And for the knees, I did 25-pound bands, and I looped it 3 times, so it would be 75 pounds of resistance over the area, which mimics 3.98 psi. And I would tell you a reason why I use different bands, but there's no good reason so far. I ran out of bands the other time. Okay, and for the shoulders, well, since the shoulder is a ball and joint, I had to come up with a different system because I couldn't just put a brace on it and then put resistance bands over it to mimic the PSI. So what I did was I took a vest, one of the ones that you use if you go jet skiing, and I grommeted holes into the elbows, and I used resistant bands across it. And the final design is that I would attach them to the back, and I would put the resistance bands in such a way so that it would be attached to the elbow and it would inhibit your motion whenever you move your shoulders. So I also looked at different things before I did the test. I looked at the time that everyone slept, and I measured on a scale from 1 to 10 how tired they were and their aches and pains. And I devised several tests to test different things. For mobility, I got some people to walk up an incline of 120 feet, and I also got some people to walk across some flat terrain of about 300 feet. And I measured things like their heart rate, see how much it increased, the time it took for them to complete the test. I measured their fatigue from 1 to 10, and their difficulty as well, or how difficult they felt that the test was. And as you can see, 300 is a long ways. And I also tried to test fine motor control by using a hammer and a pick. So I would have people go from standing to kneeling, and I would figure out how much time elapsed. I would count how many times they committed any errors, and I would also ask them how difficult they felt the test was. And the other test that I did for fine motor control was having them use a hammer and a pick to get a rod underneath a jutting object, so they would have to bend down even further. And then I did a test where it would test both simultaneously, where they would walk up a hill, they would chip off a piece of rock, they would pick up the rock, and then would return to the starting point. And I would measure the heartbeat, how long it took, and difficulty and everything else. And so there were different variables because everyone's built a different way. Everyone has a different build, health status, different gait because of how tall they are, and fitness level. So in order to try to eliminate those variables, I tried to take an average of individual performances. So I would take the differences between the performances, and then I would take an average of that, so that the comparisons between the individual person. So there were, here are some numbers. On the day of the testing, there's differences between, because I did the test on different days so that they wouldn't influence each other. I did a normalized test without any resistance, and then I did one with resistance. And this also progressed during the week, so that could also affect this. The average time slept as the days progressed at MDRS, people actually slept a little bit more. And, but they were also a little bit more tired, or they felt more tired as the time progressed at MDRS. But the pains and aches were pretty much about the same. Whenever they were doing the incline, the heart rate change was negative 14.75 whenever they did the test with the resistance and then or without the resistance and with the resistance. So it actually changed. It also trended lower. And but the time difference trended up, and the fatigue also increased from 4 to 6.25, and the difficulty also increased as well. For the 600 feet terrain, the heart rate also was less than what I thought it would be, but the time difference, or the time it took to complete the test increased. Everyone's fatigue level increased and the difficulty increased as well. And for the fine motor control, where they stood and pick up a rock and sand, the time it took them was 11.86 seconds more than the time they did it without the resistance, and the difficulty also increased on that. And whenever they were doing the overhanging rock, it took them 5.75 seconds more to complete the test, and the difficulty changed as well. And whenever we put it all together, the heart rate increased slightly by 4.5 beats per minute, and it also took them more time to complete the test, and the fatigue level and the difficulty increased as well, which you would expect with added resistance to something. So whenever I did the test, there were some things I didn't account for that influenced the results. There was so everyone slept longer, but the crew members, well, the conditions at MDRS aren't the most ideal situations, so people were still tired even though they slept a little bit more, and they were unfamiliar with the environment. The heart rate results were kind of sketchy because, as you can see in the first few results, there would be, the heart rate would be less after they used the harness that would simulate resistance. Well, I also had a lot of problems with the monitor itself. It's really hard to get a reading with the heart rate monitor. So, and in some instances, it wouldn't work for some reason. So I would try to, people would have to like put their hand on their fingers on their arteries to try to get a beat. And that's not the most accurate method of measuring your heart rate. And the harness itself actually induces a higher heart rate. The starting heart rate for everyone was a lot higher whenever they donned the harness because you have the 40-pound pack, you have the rest of the suit, and then you add the harness to it. Everyone's heart rate started a little bit higher. And so whenever you do the test, there's not much more room to go up without you pass out. The time differences on the course, they could have been a little bit skewed because, well, if I ran the test, a normal test the first time, but people also had familiarity, that's a hard word, with the test the second time, so that could have trimmed off some of the time. And that happened in a couple of the tests that I ran. People ran faster the second time with the harness, but that was because they were familiar with it. And the amount of errors that people committed, dropping hammers, stumbling, and things like that, were essentially the same with both the normal test and the one with the resistance. And the fatigue was always greater at every level, and the difficulty was always greater with every test. So the test had a few problems with it due to weather, like the sandstorm and rain and things like that. People couldn't really do the test in mud, so it was really hard to get enough testing done. There weren't that many data points available, and plus I only tested everyone on my crew once with the normal without the resistance, and then once with the resistance. So there weren't enough data points to come up with a really significant conclusion. So it would require a more prolonged experience. And as I mentioned with the heart rate monitor, there could be better methods of obtaining these measurements. So, well, obviously, memory resistance causes a significant increase in fatigue, difficulty, and elapsed time. And the reason that I wanted to do this project because I thought that added resistance would, enhance the MDR's experience. It's already a pretty good analog, and I think this would add a little bit more to it. And so now, if anyone has any questions? Okay.
Does anyone follow? You came up with a really good protocol. You came up with a really good way to test the protocol, and then you had some issues with the actual testing. Are you going to have someone next season learn from your mistakes and do the same thing? Because if you did, it would be awesome.
It would be possible, but I would have to try to get someone that was interested in doing it.
Well, I mean, there's going to be a whole new set of students coming out next year. I think you should talk to your advisors in April about coming in and do it. It's a good project to just do again and see if you can define, get a better heart monitor and see what what the results would be. Because you already did the hard part, right? They just have to actually perform your experiment.
I'll talk to her about it.
That's the way Mars Analog and Mars Research is done. So it's really awesome.
Yes, so at the site, the analog site, do you use the same spacesuits each time? And second question is, did you, in your calibration, did you account for the third of the gravity of Mars into your calibration?
No, I didn't account for the gravity of Mars. I wasn't too sure if that would affect it because, well, if you're in a bladder and speak, I mean, it would be the same as the pressure in space, well, I would imagine, but I'm not too sure about that. Everyone used the same spacesuit because at that point, everyone found the spacesuit that fit, and so they would always use the same spacesuit as well. I'm not too sure how the gravity would affect the resistance that you would feel moving in a spacesuit, though. I'm not too sure about that, to be honest.
How do you measure heart rate?
Well, I used this heart rate monitor, but that was kind of difficult because it wouldn't work all the time, and it was just this wristwatch that would be attached to your wrist, and you would touch it, and it would give you a heart rate.
There are blood pressure monitors. Maybe it might require some modification. You could get data
Right.
every I don't know, 5-10 minutes. And that can likely put that directly in the PC and get each next day. I don't know how you modify that around the trigger.
So is it just it takes your heart rate? Is there a cup?
$30.
So actually, I'm going to present on the countermeasure gravity spacesuit tomorrow. But with our study, we actually use the Scanadu Scout. That's actually it's a tricorder from XPRIZE. So that's totally wireless. You can do a whole list of biometrics, including heart rate, real time, and all you do is you swipe it on your forehead. So it's literally like a tricorder. So if you want to know more information, talk to me about it.
You would have to swipe the forehead?
All you have to do is touch your forehead and you get the whole list of biometrics that you can measure real time. So
Is there
besides
anything
heart
you
rate,
attach to the helmet so that you swipe your forehead?
well, you can actually, so it's wireless. So we can talk about it later and tell you how it works. And
Sure.
see if we can incorporate it into this next step.
Because of the trying to walk back and forth, I got to your slide that I came in on the slide where you were discussing the 4 pound per square inch, more or less, pressure.
Right.
And on Mars, is that the appropriate difference between the pressure on the outside and the pressure on the inside of the suit that you're wearing? And what were your criterion for picking that particular pressure?
Well, I picked those pressures because those were the pressures in the spacesuits, and so those are the spacesuits that they use now regularly. So that's the pressure I was aiming for. I didn't consider the 3/4 gravity. I was just working with the spacesuits that we have currently available and what their operational pressures were.
And another question: how long do you expect people to wear these space suits at a time? Hours, days, minutes?
It kind of depends on what they're doing. I'm not too sure. Like whenever we donned our spacesuits, we only went out 3 or 4 hours at a time because anything more than that is pretty taxing because you're lugging around this pack and it's heavy, and you run out of water, and there's a bunch of different other factors that would make you want to return to the have.
Let me point out to people who study this sort of thing, I used to be a whitewater boater, person that went down streams, went down big stuff. So we used to wear wetsuits, but we were out of the water in case we wore the wetsuit in case we fell into 0-degree centigrade water. So there you are, and after half a day in that, you got to take the wetsuit off, folks, and the stink is unbearable. And so one of the things that I never hear discussed when people talk about these suits is how they're going to handle that problem. It's a real problem, and it's a problem that some of us have actually dealt with. And I like to have the people who are doing these other studies take that one into account also, please.
My presentation tomorrow.
Are there any more questions? Are there any other questions? Oh, okay, all right, I guess so.
So, describe to me again the actual movements that were needed. Was it just flexing of the knee joint,
Yes.
flexing of the elbow joint, and then the movement of the shoulder?
The shoulder, it was if you move your shoulder forward or you moved it up a little bit, or any frontal movement with the shoulder, it would be inhibited. Obviously, if you went back this way, since the resistance bands will be loose, there wasn't any resistance there, but I don't foresee a lot of people trying to do that in a spacesuit. So it was all this forward, and that was all inhibited. Because once you started moving forward, it would catch on your back, so there would be tension there, and that would create the resistance.
I think we have to clarify that these spaces are just simulator spaces. They're not really like real spaces that they are.
Yes, they're
These
just
are real,
overalls
just
out
simple
there.
simulation. It's not.
Yes.
It's not real spaces per se.
Any other questions?